Let's write some recursive list rules. The double list 2 is going to double each element in a list. My base case is if I have an empty list, then when I double it, I just have the empty list. Now the recursive case, I'm going to have a list, so I'll have a head and a tail, and my result I'm going to put here, but I'm going to leave this blank for now, and we'll come back to what we're going to put there. The first thing is that I need to double the head. So I'll do that with some math. I'll say h2 is h times 2. And then I'm also going to need to double everything in the tail. So that's a recursive call. And that'll give me, I'll call it T2, so that everything is doubled. So now the question is, what is this result? Well, the result is the head put in front, or head 2 put in front of tail 2. So h2, which is 2 times the original head, and the tail is going to be the tail with everything doubled. So this completes my rule. So let's consult. Did I call it double tail? I did. That's what happens when you talk and type at the same time. So now when I double the list, you can see every element is doubled. I could also, instead of doubling the list, I can duplicate the list elements. So here, in my recursive case, I'm going to have a head and a tail, and I'll leave the result for a moment. I don't need to do anything with the head yet, but I do need to duplicate the list elements in the tail. And then my result is going to be 2 copies of the head element with the tail after I duplicate everything. So let's consult. Did I say elements? Elements. So I'll duplicate list elements, and something bad happened. Duplicate list elements, yes. So I'll answer yes. And so there you see A, A, B, B, C, C, D, D, E, E. And whenever you see this, it just means that the list was too long and it gave up trying to display it. So don't be alarmed if you see that. As long as your list starts out looking good, then you'll be okay. So next to, we'll check that 2 elements appear next to each other in a list. My base case is not going to be an empty list here. If I have X and a Y, they need to appear next to each other in the list somewhere. I don't care what the tail is in that case, because now X and Y do appear next to each other. Otherwise, what I'm going to do is I'm going to get rid of the head, and I'm going to look to see if X and Y are next to each other in the tail. So I'm not actually returning a list here, I'm just returning true or false. So we consult, and now let's So in the list A, B, C, 1, 2, 3 are A and B together. That's true. Okay, so what is A next to? B and nothing else. So what if we say, we'll say AX here. So that's true. And I didn't give these variables. So let's say A is next to X, B, X, and false. So it actually, when I rejected it, it kept looking for something else that atom could be next to. If I give it a list that's too short, it doesn't match that base case. The base case, we have to have at least 2 elements, and those would be the 2 elements that we are looking for next to each other. Let's write some methods that do some summing. So this rule is going to sum the elements of a list. So the sum of an empty list is our base case, and that sum is going to be 0. Then, to sum the list with some head and tail, we're going to get a sum. But to get that sum, first we have to sum the tail, and that's going to give us the sum of the tail. Then the final sum that we're going to return is sum t plus h. I can also write a rule that sums the first x elements of a list. And that's actually going to take 3 parameters because I need to pass in how many I want them to do. So sum first x. And in here, I don't care what the list is. If I'm summing the first 0, that result is 0. So it's almost like that's the base case where there's an empty list. There's nothing left to sum here. My recursive case, I'm going to have some list. And again, I don't have to check that it's a list. If I give it this list syntax, the only thing that would match here is a list. The first x elements and the sum. So now I'm going to say x1 is x minus 1, and that's going to allow me to find the sum of the first x minus 1 elements of the tail. And that gives me the tail that I get from the sum that I get from the tail. And then the final sum is going to be sum tail plus h. So notice here, I'm subtracting 1 from x each time as I go through the tail because the first 3 elements of the list include the first 2 elements of the tail. Let's test them. So it's saying operator expected. There we go. So now if I sum list, it adds those up, and you can verify that that's correct. So if I sum the first 3, I get 6. If I sum the first 4, I get 10, and so on. Not every list operation has to be recursive. So I can write a cons rule that takes an element in a list and returns the pair element list. And if that actually work just like cons and scheme, because if I cons the element with a list, it'll return a list. If list isn't a list, then it's going to be a pair. It'll be a pair anyway, but in that case, it wouldn't be a list. It would be a non-list pair. If I want to duplicate the head, and I have head and tail, then I'm just going to unify that with 2 heads in front of the tail. And both of those rules don't require a lot of logic to them. So cons ABC gives me the list ABC. Cons A and B gives me the pair AB. And if I cons the list 1, 2, 3 with the list A, B, C, there I get the list 1, 2, 3 is the first element, then A, then B, then C. So list size will return the size of a list. Now there's a built-in method that will do this, but we can build this from scratch as well. So the empty list has size 0. Then for a list, we don't care about the head. We do care about the tail. The size is going to be the size of the tail plus 1. So once we find the list of the size of the tail, then we can add 1 to that. That'll give us the size of the entire list. And of course, as it recurses through this, it'll find the size of the tail the same way. I can write a rule, add 1 to all. This increments each element in the list. Base case there. The empty list, we're done. So it's just going to be the empty list. There's nothing to add to. Otherwise, we're going to add 1 to all. So now we have a head and a tail. And we're going to add 1 to the head. And we're going to increment everything in the tail. So we need to do that in the body of our rule. So H1 is straightforward. It's H plus 1. And then we need to add 1 to everything in the tail. And that gives us T1. We can also write a more general increment rule. Here, we can say, try to use add 1 to all. So if we get a list, and to check that we have a list, we're going to only match a list as the first parameter. So then this list variable, all we need to do is add 1 to all. And now we need to pass the list. But remember, we broke it apart in our parameter, so we need to put it back together here. So this is a complete list. And that's going to give us our result of a list. So we use that previous rule to generate the result here. But what if it's not a list? Well, in that case, y is x plus 1. So let's consult. We have a singleton variable. It looks like I reversed my names here. So the list size here is going to be 1 plus 1. So I have something weird with my assignment. Oh, I did equals. This should be is, so that's a good reminder. Is what actually does this operation and then unifies it. If you'll see here, what I did was I had a whole bunch of plus ones. I'm basically saying unify it with this with 1 in the end. So we don't want to do that. And that gives me the result I want. If this isn't a list, I get false because that doesn't have a list size. So now I can add 1 to all. I can also increment that. I could also just increment one of the numbers. So notice that rule works for lists or integers. Okay, so let's do a few more. So here's sort of like a filter type rule. We're only going to keep multiples of 3. So if we're given the empty list and we remove all the multiples of 3 from the list, we get the empty list. If we're given a list, we have a head and a tail, and we're going to put the head back on the rest of the list, the recursive result list, only if 3 divides h evenly. And we're going to get the multiples of 3 from the tail and put that in T1. Another case would be if this is not true. So x is h mod 3, and x is greater than 0. Notice in this case, we don't put the head back on, we just get the multiples of 3 out of the tail. So that's a case where we have multiple conditions, and depending on the condition, that determines how we build the result list. Another example similar to that, we're going to remove every other element from a list. So, base case, and also if there's just one element left, then we'll just return the list with that one element in it. And I need to spell that right. Then if I remove every other element, now here, there's at least 2 elements in the list because I've checked the case where there's 1 and 2. So now there's something on the list, and then there's that every other one that I'm going to remove. So I don't care about that element. And I put the list back on. I put the head back on. The second element I throw away. It's an anonymous variable. And then I'm going to do a recursive call on the tail, and that'll be the tail of my result. Let's consult. Let's take that list we did before, and we'll say only mults of 3. That gives me 3 and 9. It gave me false because I said no. If I just said enter, that would be okay. And then I could also remove every other from that list, and that gives me 8, 2, 9. If I had one more element, that would also be there. I think I had a longer list above. Yeah, so let's remove every other one from this one. Yeah. Okay, so the last example we'll do with this video is we'll talk about sorting. So first off, let's check to see if a list is sorted. So the empty list is trivially sorted. A list with just one thing in it is trivially sorted. So that's an anonymous variable because I don't really care about it. And a list is sorted if, so here's what we're going to do. First off, the tail is going to have to be sorted. I'm going to have something in the head, we'll come back to that, and the tail. And the tail has to be sorted. So if I say H here, actually I don't really care about H, right? So let's just try it like this. Let's see, is sorted. True. Okay, good. Well, is it good? That's also says true, because what we just basically said is this a list with at least one element in it? So really what we need to do is we need to say H1 and H2 are at the start of the list, and H1 is less than H2. Right? Do you see that? Because we need to make sure that the first two elements are in sorted order, and then the rest of the list is in sorted order. So let's try that. False. Okay, good. That's what we wanted. That's also not sorted. But that is sorted. 1, 2, 3, 4, 3. Well, that's clearly not sorted. So why is it saying true? Well, notice here we're saying if these two elements are in order, great. Look to check that the rest of them are in order. But H1 is in order, but H2 might not be. So we want to put H2 back on the list that we checked to see that's sorted with that recursive case. If I consult that, that's not sorted, but that is. So now my is sorted rule works the way I would expect. So there's a neat thing in Prolog. Say I have a list 1, 2, or let's say 3, 4, 5, 2, 1, called permutation. Interesting. Did I misspell that? There we go. I misspelled it somehow. So notice if I keep giving this over and over, it'll give me every permutation of the values in that list. So I can actually use that to sort a list. Permutation sort. For those who think bubble sort goes too fast. So my permutation sort is going to get a permutation of X, and that'll be Y, and then I'm going to check is sorted Y. And that's my sorting algorithm. So when I consult, I can say perm sort, and I misspelled it again. Okay, there we go. And notice it sorts it. So you'll notice though, this sort's very slow because I'm basically shuffling the list each time and then checking to see if it's sorted. And if it is, I'll go back to the code because this will take a while to complete. It makes a permutation, checks if it's sorted. If it's sorted, the rule succeeds. If it's not, we get a different permutation. So you can think of the complexity here is basically n factorial because that's how many different permutations there's going to be for the list. So of course this is going to be incredibly slow, but it works. And we'll talk about some other ways to sort later in the semester.